All right, guys, we are going to talk about friction. So today you completed a lab with friction, and you basically were looking at the relationship between friction force and normal force. And specifically, I wanted you to look at the slope of a line. So we were talking about, we should have had, draw for you. You should have had like force friction here, force normal here, and you should have got some sort of line. This line actually represents something. This line represents what we call our coefficient of friction. So the coefficient of friction is a unique value. It's basically a ratio between our friction force and our normal force. It's kind of like the stickiness of a surface. So when I'm talking about the coefficient of friction, you're going to hear me talk about this a lot. What it says here, the ratio of the normal force ends up being converted to frictional force. That's basically the stickiness of the surface. This coefficient of friction here, it's the Greek letter mu, mu, kind of like the Pokemon. But the coefficient of friction, or mu, it doesn't have a unit with it. So it's one of the few things that we will not see units for, because if I were to divide force normal to the other side, force friction and force normal both have the unit of newtons, which cancels out, which leaves mu without a unit. So that's why there's no unit there. Hopefully this graph up here looks familiar. This should be kind of like what your graph in the lab you were looking at. Not the one you came up with, but like one you were getting your data from. Now, there are two, but technically three types of kinetic coefficient of friction. There's static friction, and then there's kinetic friction. So we should have a coefficient of static friction, and we should have a coefficient of kinetic friction. Now, you'll see here during this static section, your force, this peak right here, that's going to give us our, that's how we get our static friction. Static friction is basically that friction that's going to keep us from moving. And then there's a peak, and it's going to drop to the kinetic friction, that friction while we're moving. So as I said, there's three types of friction. Static friction, if you think of like static, or I think stagnant water, like not moving, it's the force that's going to keep an object from slipping. So this, when we do our calculations of force friction, it's going to be less than or equal to the coefficient of friction times our normal force. However, kinetic friction, this is the friction when an object's moving. Imagine I'm pushing a box across the ground. So I've got like a box here and I'm pushing it. This friction the other way, that's my kinetic friction. This is going to be equal to the coefficient of kinetic friction times normal force. Now you'll notice here that these two, they have different subscripts because they're going to be different numbers. Your coefficient of static friction is always going to be greater. So in a situation, let's say it might be 0.6 for a surface, and then the kinetic friction might be 0.4. The third type of friction we have is rolling friction. So we're going to kind of save this for later in the year, but I want you to be aware of it now. This rolling friction is basically when an object's rolling. It is moving, but it's specifically rolling, not necessarily just sliding across the ground. So I want to start with an example. This is example number 1. And basically, we're going to look at Sam pushing a wooden box. So Sam's going to push a wooden box. I'm going to start by drawing a picture just to wrap our mind around the situation. We've got an applied force, and that's what's happening. So I'm going to be a little more specific and draw my force diagram. We have normal force going up. We have force gravity going down, force applied, and force friction. So our problem says Sam pushes a 10-kilogram wood box across a wood floor at a steady speed of 2 meters per second. How much force does Sam exert on the box? And it tells us the kinetic friction of wood on wood is 0.2. Now, before I even start this, I want to ask you, what is the net force if my object is moving at a steady speed? My net force should be equal to 0. So I'm going to start the whole thing, and I want to sum my forces in the x direction and then the y direction. So we're going to color code this. Sum of forces, I'm going to start with the y direction. In the y direction equals mass times acceleration, which gives me force normal minus force gravity. Then we're going to do the x direction. So my sum of forces in the x direction equals mass times acceleration, which gives me my force applied minus force friction. Now our end goal is how much force does Sam exert on the box. So we really want to solve for this applied force. So I'm going to mess with this side first. Since we're moving at a constant rate, my acceleration is 0, so that whole side becomes 0, which gives me force applied minus force friction. So if I want to solve for my force applied is equal to my force friction. Now, really, what does force friction equal? We don't have this information, so we need to substitute this in. So force applied equals, and we're going to substitute in our equation, kinetic friction, coefficient of kinetic friction times force normal. But now we need to solve for force normal. So we're going to use our vertical side. Now in the vertical direction, we don't have an object accelerating off the ground, so it's going to be 0, which gives me force normal minus force gravity. I can set these two equal to each other since they're equal to 0. So force normal equals force gravity. And remember that force gravity is going to equal m times g. So force normal is equal to m times g. Now this is not always the case. Literally the next example we're going to do, this is not the case. However, since there are no other forces acting in the y direction, this is true. So I can say force normal is equal to 10 kilograms times 9.8 newtons per kilogram, which gives me a normal force of 98 newtons, which I can then plug into the other side. So force applied equals my coefficient of kinetic friction, which is 0.2, times my 98 newtons. This gives me an applied force of 19.6 newtons. There we go. So this is one of the simpler examples. We technically have done this problem. I just haven't broken that normal force down. I've always given you the applied force and not the normal force, that friction force. We've done this problem before. Now we're just taking it one step deeper. So what if we don't have this force applied in the x or y direction? What if it's applied in an angle? So that's the next problem we're going to look at. So our next example, a box with a weight of 50 newtons experiences a force of 40 newtons that's 30 degrees above the horizontal. If the coefficient of kinetic friction is 0.4, what acceleration does the box experience? So we basically want to know what's the acceleration of my box. So I'm going to start this problem by drawing my force diagram pretty much every single time I start a problem this way. So I get force normal, force gravity, and then I've got some sort of applied force up in that direction. And I'm going to have force friction acting in the opposite direction. Now, when I get a problem that has any sort of angles at it, I'm always going to break this force into the x direction, and I'm going to break it into the y direction. Now, when I'm looking at this, I've got a triangle here. Let's redraw it right color. I've got a triangle here. I've got my force that's applied, I've got force y, and I've got force x. So if I do some trig, we've got an angle here. This is my opposite, this is my adjacent, and this is my hypotenuse. So if you remember good old SOHCAHTOA, we can actually solve for what each of these components would be. So if I say that sine of theta equals my opposite Fy divided by my hypotenuse F, I can solve for what Fy would be. Fy is going to be equal to the force applied times sine theta. I'm going to highlight that because that's an important thing to know. Then I can solve for what my x direction would be. Cosine theta is equal to f of x divided by my force, which if I want my x direction, it would be fx equals f cosine theta. Now these can work anytime we're doing a problem like this. However, I do want you to show me the process of you getting to this. So now I'm going to go, same situation we've been doing, and I'm going to sum my forces. So I'm going to start with the x direction this time, because we want our acceleration in the x direction. So I'm going to say sum of forces in the x direction is equal to mass times acceleration, which gives me my forces in the x direction minus my force friction. Now you'll notice I'm not using this force applied, because once I decide to work in the x and y directions, I'm only going to work there. So that's why I write Fx instead of F applied. Now let's look at the other direction. I'm going to work a little bit down here. Sum of forces in the y direction equals mass times acceleration, which gives me force normal plus the force in the y direction minus force gravity. So you'll notice here that force normal is not equal to force gravity because we have another force in that direction. Now my end goal is to get this acceleration right here, this horizontal acceleration. However, I kind of need to fill in the pieces to get there. Now we've got a situation here where our box has a weight of 50 newtons. This is not kilograms. This is basically telling me my force gravity here. So my force gravity is 50 newtons. So if I want to change that to figure out my mass from here, I need to say that force gravity is equal to m times g. So 50 is equal to my mass times 9.8, which means my mass here is going to be equal to 5.1 kilograms. Sorry, I ran out of room on the edge. So I'm going to get 5.1 kilograms times A, which is what I'm solving for, equals Fx, so I'm going to plug in that F cosine theta, minus force friction. Well, I don't know what my force friction is, but I do have the coefficient of friction, so I can say F times force normal, mu times force normal. But we don't know what force normal is. So we've got a lot of issues here. We don't have force normal. I don't have it to get to acceleration, so I have to go and solve for force normal before I can even do that. We're going to use the vertical side to do that. Now, in the vertical direction, my object is not accelerating. I don't have an object just flying off the ground in the vertical direction. So I can set that equal to 0 equals force normal plus Fy minus force gravity. And I want to solve for force normal, so I want to get it by itself. So I'm going to add force gravity to the other side and subtract force in the y direction. So that gives me force normal equals force gravity minus Fy. Force normal, we know that we have a weight of 50 newtons minus, and then I'm going to figure out what my force y is, which is going to give me F sine theta. So that gives me force normal equals 50 minus my force, which my applied force was 40, times sine of my angle, which was 30, which gives me force normal equals 50 minus 20, which we've got a force normal of 30 newtons. So now I'm going to take that and plug it back in up there. So 5.1 times A, I'm going to leave my units off, equals, and we're going to plug in what we know for our applied force, 40 cosine 30 minus 0.4 times 30, my normal force. So I'm going to plug this on to the calculator. This gives me 34.64 minus 30 times 0.4 is 12 equals 5.1A. 30.64 minus 12, that gives me 22.64 equals 5.1A, which gives me an acceleration of 4.44 meters per second squared. So our problems just suddenly got a lot more difficult because we're solving for, like, we've got the x and the y direction. They communicate with each other and they impact each other. So it's not just as strictly we solve for either the x or the y direction. Because that normal force is part of force friction, it makes these two sides really work together. So that was if we were having an object pulled up at an angle. What if we have an object that's pushed down at an angle? So this is the exact same scenario as up above, but instead of being pulled up, it's going to be pushed down. So now we've got the exact same thing. A box of weight 50 newtons experiences a force of 40 newtons, but it's 30 degrees below the horizontal. If the coefficient of kinetic friction is 0.4, what is the acceleration of the box? Same situation. So I'm going to start the exact same way I did last time, drawing my force diagram. So I've got force normal, I've got force gravity, I've got my applied force downward, and then I have force friction, acting in the opposite direction of motion. I have my X component of this force, and then I also have my Y component. So I'm going to jump straight to summing the forces this time. The sum of the forces in the Y direction equal mass times acceleration, which gives me, now I'm going to do all the Y direction. So I've got a force normal pointing up, Fn minus Fy minus Fg. Now this time force in the Y direction is pointing downward because it's got a downward component of this force now. In the X direction, I've got my sum of my forces in the X direction. I'm going to actually move this over here because I know I'm going to need space. Sum of the forces in the X direction equal mass times acceleration. That's the acceleration I'm solving for, which equals Fx minus Ff. So we kind of have the same situation. My X and Y components are still calculated the same way. We've still got these equations that we used up here. These two, I can still use this because it's still a triangle. So I can rewrite this to give me mass times acceleration equals F cosine theta minus mu Fn. Again, I don't have Fn. My mass didn't change about the situation, so it's still 5.1a equals my 40 cosine 30 minus mu, which we know that, 0.4, and I still need that normal force. So we need to figure out normal force using the vertical direction. M times A. My object's not going to suddenly accelerate off the ground, so we've got 0 here, equals Fn minus Fy, but Fy is really F sine theta, because we can do some trig there, minus Fg. And we want that normal force. So to get normal force by itself, I'm going to add the other two forces to the other side, which gives me force sine theta, that's my applied force, plus force gravity. Fn, so that gives me my 40 sine 30 plus 50. So that gives me a normal force of 20 plus 50. So now my normal force is 70. Now I ask myself, does this make sense? If I'm thinking about it, does it make sense that this normal force is greater than up above? I've got two forces going downward and one force upward. But before, I had two forces upward and one downward. Does that make sense that my normal force is greater when something's pushing down on it? Does it make sense that the ground has to support my object more? So let's keep on plugging ahead. So now this normal force down here, I'm going to plug in 70. 5.1a equals that 40 times cosine 30, but the same number comes out, so we still get this 34.64 minus, however, now we've got 0.4 times 70, which gives me 28. 5.1a equals 6.64, which gives me an acceleration of 1.3 meters per second squared. So I want you to ask yourself, every time we do a problem, does it make sense that my acceleration this time is less than the acceleration before? If I have something that's harder, it's the same object, but I'm not pushing it in the optimum angle, doesn't that make sense that it wouldn't have as much acceleration? All right. I will see you guys in class tomorrow.